Hello. Hi.
Yeah, this is
So we just start from here, or do we have anything?
yeah. Please go ahead. Whatever you have on your agenda.
Okay.
Uh, Perhaps we'll wait just maybe 1 or 2 minutes for a couple more people to trickle in.
Yeah, sure thing. I'll just start or test sharing my screen.
That sounds good.
I hope everyone is able to see my screen.
Yep, we can.
And my audio is good, right?
Yep.
Yeah.
Okay. Let me know when should I start.
We'll give it till 7:02, perhaps. And then this will be recorded. So anybody who misses any bit of it, then they can go back and watch that. So it shouldn't be too big of a problem. Okay, we should be good to start now.
Okay. Hello, everyone. If you don't already know me, I'm Deepak Khatri from Upside Labs. I started Upside Labs started working on Upside Labs back in 2016. And we have been making good hardware since 2020. Before that, it was just me trying to build homebrew biopotential amplifiers. I started with BioAmp version 1 and released it on 10-day in 2018. Before that, I presented a crude design of basic BioAmp, you can call it version 0 in 2017, and I presented it as a very low cost biopotential amplifier for prosthetics, human computer interface, and things like that in 2017. It was kind of a presentation opportunity at my university. And since 2016, I have been working on the designs. So it was an iterative process. I learned a lot during the process, and some things I can share with you that will help you to design your own BioAmp. So basically, this pre-workshop is on designing or understanding how a biopotential amplifier that is basically the device we create at Upside Labs, the BioAmp, and how to do the signal processing or the signals you are going to record from your biopotential amplifier for human computer interface and brain computer interface. Basically, I'll try to bring your neuroscience skills to another level. If you don't already know the biopotential signal that generates from your body, it includes your EEG, EMG, ECG, EOG. The frequency bands we have mentioned here are debatable, but basically EEG is a signal, or EEG is electroencephalography, a signal generated from your brain, comes in a frequency band of 0 to 42 hertz or something like that. And this EEG is used to basically create brain computer interface like your Neuralink and such. Then we have EMG or electromyography that comes in the frequency band of 70 to 500. Some scientists claim to be around 0 hertz to 2000 hertz and something like that. So it is debatable. You can check online, and maybe you can create your own biopotential amplifier with very wide band and let us know your results. Then we have ECG or electrocardiography, that is a signal generated by your heart. Basically, a sinus rhythm is created which travels to your other part of your heart and create a ECG, that basically the signature that your heart is beating, and it comes under 0.5 or 0.05 hertz to 150 hertz. When we record this ECG, we usually tend to go with 0.5 hertz to 40 hertz or 45 hertz to reduce the 50 hertz and 60 hertz noise. Most of the time it is to reduce your 50 and 60 hertz noise. Then we have electroculography or EUG, that is basically the signal generated by the signal generated by your eye. Basically, your eye has a dipole or polarity, and when you move your eye, the polarity creates a deflection, and you can record it on the surface of your skin. This signal is also debatable, but it comes under 0.5 or 0.05 hertz to 20 hertz. This is a very simplified version of a human computer interface we tend to use at Upside Down Labs. Biopotential signals generate at a human level on your skin. We record everything non-invasively. So your biopotential signals includes ECG, EMG, EOG, and EEG that originates from your cells inside the body. These biopotentials comes in various voltages, and EEG is very minute in microvolts. Then you have EMG, which is very prominent on skin near your muscles, and it comes around some millivolts. And to create a human computer interface, you basically create a biopotential amplifier or BioAmp. This is basically the part which is your BioAmp. First, you initialize the recording process or the connection process via a filter. It is a low pass filter to reduce the high frequency interference noise. Basically, the noise created by all the EMI generating devices around you. That includes your mobile phone towers, and your tube light, things like that. So basically, we want to reduce the signals that are going to be picked up by our biopotential amplifier, because the electrodes that we are going to use with the biopotential amplifier acts as antennas, and they usually picks up these signals quite well. So we filter the input signal via band low pass filter. Then we have an instrumentation amplifier stage. Instrumentation amplifier is a neat little hack you create using not basically hack. It is a very detailed and very well studied design for increasing the common mode rejection ratio of your instrumentation of your basic general operational amplifiers, and increase its input impedance. You want both to be high. CMMR should be more than 100 dB, and your input impedance should be in some 100 mega ohms to like provide a very low path for the current to be flown from your skin to the amplifier, because your skin impedance is in some mega ohms and you want the amplifier to not load the skin. Our BioAmp example is around 1 giga ohms, and above that it doesn't load the skin at all. And CMRR, which is common mode rejection ratio, is more than 100. Then we take the instrumentation amplifier output and pass it through a band pass filter. basically we try to use what we have here. So we create a hardware band pass filter that will allow these bands to be passed through the filter and remove all the other and discard everything as noise. Then the band pass filter signal will be applied to the ADC, which is your analog to digital converter. These ADCs will either be connected to a MCU microcontroller unit, or these can be standalone units directly connected to your main computer. These are basically used to convert your analog signals to digital signals that a computer can read. And this entire setup is basically your human computer interface. You start with the signals generated from human body and you convert it to computer readable values so that you can infer some basically infer some information from the signals you are going to record. That includes EEG based data for meditative data, as in if you are focusing, if you are sleeping and things like that. Your ECG data like your heart rate, and if you have any heart ailment you can detect that also. For EMG you can use the signals for healthy patients to improve their workout, and other patients like for patients who lost their limbs to create prosthetic arms. So you can create a human computer interface in a way that you record the signal from the remaining part of the muscle, and you try to infer some information from the signals to control motors in a way that you can create a prosthetic arm. Then for EOG you can create low latency game controllers and other peripheral devices that augment the human capability in a scenario where other means of communication with the computer are not available. Basically, when human is paralyzed, you can use EOG signals. Most of the time, your eyes will still be functional, so you can create a EOG based interface between a human and a computer to provide some ability to control the computer or provide information to the outer world just by blinking. Then we covered EEG, EOG, EMG, and ECG. For a BioAmp hardware design, this is mostly how we design BioAmp at Upside Down Labs. There are various different methods, and this is what I came up after years of designing biopotential amplifiers and trying to build a very sophisticated piece of hardware that can record your biopotential signals in a way that you can easily able to record EEG signals, because EEG signals can be the hardest signals to record because of the way we use electrodes. We don't have very direct connection to most of the brain, and we tend to use either gel based electrodes, and if you go with dry electrodes it creates or makes the impedance very high. The electrode impedance should be low, the instrumentation amplifier impedance should be high. So by electrode impedance I mean the connection between the electrode and the skin should be lowest possible so that we can record the signal easily. So if you want to create a biopotential amplifier, choose the best suited operational amplifier. Quad operational amplifier is recommended for your specific application. We will talk about the characteristics. You will look into the operational amplifiers in later slide. Then you have to do some calculation that includes calculation for your instrumentation amplifier and the band pass filter. For instrumentation amplifier, you go about setting up the gain for that instrumentation amplifier. We usually keep the gain at 11x, And for the band pass filter, we change it around. For EMG, we keep the gain at 200 with a frequency band of 72 hertz to 720 hertz. Then for EEG, we keep the gain to 1000, and we keep the band pass filter from 0.5 hertz. We try to go till 0.5 hertz, but some parts usually, or how we use the part size limit us in that way. So we only have 3.3 hertz to a specific endpoint that is around 40 hertz to 45 hertz. This biopotential amplifier that you create for brain can also be used for your heart and your eye. The overall gain for your EEG system, that includes your brain, heart, and eye, biopotential amplifier will come around 11,000 gain. And for your EMG biopotential amplifier that I talked about, with 220 gain for band pass and 11x for your INA, will come around I think 2,400 something. Then we convert everything, but we have calculated what we have finalized for the operation amplifier into a schematic. In KiCad, we use open source softwares for all our designs. So for schematic design, we use KiCad. Then for layout, we also use KiCad. It's basically the same EDA suite. Finally, we have our PCB. We will look into the schematic layout and how the PCB looks in later slides also. For quad operational amplifier, you look for CMMR to be more than 100 decibels for a good result. That will eliminate your interference noise, your 50-60 hertz noise very easily. Even if the charger is connected, our BioAmp chip doesn't pick up 50-60 hertz noise in most scenarios. If the impedance of the electrode is very good, you will not see any deflection or any 50 hertz noise. Even if you don't use any software filter, you will not see any 50 hertz noise. Minimum operational voltage of your quad operational amplifier or any operational amplifier you are going to use, you can also use 4 discrete operational amplifiers. Should be less than 5 volts because all your MCUs, like your Arduino, works on 5 volts. If you are going towards other modern microcontrollers, they are going to work with only 3.3 volts. So try to find a operational amplifier that works around 1.8, 2.7 volts. Start working at 1.8 to 2.7 volts and works at least till 5 volts. So it shouldn't be less than 5 volts, and it shouldn't be more than 5 volts if the maximum operational voltage is considered. Then you look for the package for your IC. If you are trying to do a DIY setup for the biopotential amplifier, go with PDIP or plastic dual inline package for your operational amplifier, like your LM324 is a good option. If you are trying just for the EMG, you can try LM324. For your EOG and ECG, you can try TL074 at a higher voltage. Then you can use like the old TL074 start working at 7 volts. So I don't really recommend that, but if that is the only option, you can use it with higher voltage. Let's say at 9 volts, you can use a 9-volt battery. Don't use any power supply or any power adapter to power your setup while you are developing the BioAmp. Then if the chip has EMI hardened characteristics from the manufacturer, it is better in noisy environments. Let's see how to create your instrumentation amplifier using discrete operational amplifiers. There are 2 options. One option is a 2 operational amplifier instrumentation amplifier design that is used in the BioAmp XGPL. For this design, you basically need 4 resistors and 2 operational amplifiers. These 4 resistors, R4, R3, R1, and your R2 are required. This RG is optional. It is to set the gain only. So this is a very simplistic design of an instrumentation amplifier, and if you are trying to create something from discrete components, and you don't have laser precision for setting up the resistors value, so this is the best option in our use case, because you have very less chance of using mismatched components and degrade your CMMR. So basically, if you use components with you basically use all the components with 1% or better accuracy. If the components are not matched, your common mode rejection ratio will degrade a lot, and you will see a very noisy output, and most of the times you will see just the noise. Even if the signal is there, you will see just the noise in scenarios where AC appliance is very close to it. Second option is your 3 operation amplifier instrumentation amplifier design, which is used in BioAmp version 1.5. All the terms I am talking here, BioAmp EXGPL, BioAmp version 1.5. If you are not familiar with these, you can go to github.com/upsidedownlabs and look at the open source files for these designs. I will share a link. Basically, my partners will share the link for a BioAmp EXGPL and BioAmp version 1.5. In this 3 op-amp design, you have to use at least 6 matched resistors and 3 operation amplifiers. These resistors R6, R5, R3, R1, R2, R4, these should be matched. These should be same, these should be same, and these should be same. Then only your your instrumentation amplifier will work in a way that you will be able to record biopotential signals in a clean manner. Then you have your RG here, which is not optional in this case. You have to use a resistor to set the gain. All the calculation for these 2 operational amplifier and 3 operational amplifier design can be found in the Texas Instruments Analog Engineer Circuit Cookbook for amplifiers. On page 27, you will find the 2 operational amplifier instrumentation amplifier design, and on page 31, you will find 3 operational amplifier instrumentation amplifier design. This is a schematic of a BioAmp EXGPL. You have your 2 operational amplifier instrumentation amplifier design. Basically, this resistor should be matched. This resistor should be matched. Then on the back of the BioAmp EXGPL, you will find that there are 2 pads where you have the ability to change the gain. So RG is optional, so we have provided pads for this component. Then we have 1000x gain band pass filter. If you do the calculation with the equation provided in the Texas Instruments design cookbook for amplifiers, you will find the gain for this instrumentation amplifier is 11. Then for this band pass filter, we have used a high pass filter here and a low pass filter here. So this is basically a active band pass filter, and this band pass filter which we have used in BioAmp EXGPL is very narrow, but it allows for all the biopotential signal to be recorded. Okay. Then to create or to set a reference voltage, we usually tend to go with whatever we provide to the microcontroller divided by 2, so VCC by 2. For that, we use 2 resistor dividers to create a voltage divider at the midpoint of the VCC, and we use a buffer to create an amplifier reference, and the same reference is used for human also. So basically, third wire which we use for all the biopotential amplifiers is a bias or the reference. This reference is VCC by 2. If you are not understanding what I am saying in terms of what is VCC, what is this driven right lag, these are some terms you can basically find on Google. If you don't find that, you can contact us at contact@upsidedownlabs.tech for any further information. We'll be happy to guide you through the process. Also, you can create issues if you find some discrepancy in the repositories or the projects we are creating. That includes BioAmp HCI, BioAmp version 1.5, and some more hardware projects are also coming in DIY form factor. That includes BioAmp Biscuit, BioAmp Candy, and BioAmp Patch. After designing your schematic, you go ahead and create a layout like this. You have components with pads. You create wires to connect all, or you route wires between the pads wherever you have like made the connection in the schematic. Finally, you will get a PCB like this. This is our BioAmp HCI bare PCB. Then this is how the BioAmp HCI PCB looks after assembly. This is a ECG signal we recorded using BioAmp HCI, a very early version of BioAmp HCI. Then this is the EEG signal we recorded with BioAmp HCI. There is not much to see here, but we'll show you a better demonstration of the EEG signal. Then this is EOG. Whenever I move my eye, the dipole changes, and with that polarity change, you see the signal on the screen. This is the EMG. Whenever I flex my arm, you can see the signal. If you are using a chip that is that can work on 5 volts, it is good to go with your Arduino Nano and Arduino Uno. If the Biopotential chip you have created only works like above 3.3 volts, this is the best option for you to use Arduino Nano or Arduino Uno. Even if you want to use the Biopotential chip with 3.3 volt compatible devices, you can do that. And this is how the circuit will look like. Excuse me. So if you want to connect the BioAmp HCI to your ESP32 board, this is how you connect. You use voltage dividers or a resistor voltage dividers to create a pathway to convert 5 volt to 3.3 volts using 2.2 k resistor and 1 k resistor. And you can use very small boards like your Adafruit QT to create a very small like setup for recording your EEG signal, EOG signal, EMG signal, or EOG signal. If the previous connection diagram was not clear enough, let's see it here. When you output the signal, that output would be 5 volts because we are delivering the VCC at 5 volts. If you divide the 5 volt in a portion of 1 and 2.2, you will find that it is now compatible with 3.3 devices also. You can find the calculations, entire calculation, and how we use the ratio divider method to convert the sensor output from 5 volts to 3.3 volt on online platform also like Google and let's see the connection you have to make for some of recording some of the vibrant signals. For EMG, we usually tend to go with ulnar nerve because this is a very prominent nerve which can create very high potential spikes, and this is most accessible in our like practical scenario. So we use ulnar nerve to record EMG signals. What I have shown in the previous demonstration, you see, I'm using ulnar nerve signals one. Then we have EOG biopotential recording setup. For that, you tend to go with either your vertical recording or your horizontal recording. This is how your EEG recording setup will go if you are going to use BioAmp XGPL with your Arduino Nano. This is for your vertical, this is for your horizontal movement recording. In horizontal movement recording, you basically can detect the gaze of the eye, and for vertical movement recording, you can detect blinks very easily. For ECG, you have two options. You create a path around the heart, as in you connect electrodes one here, and a reference can be connected below your hand. And these are not the only spot where you can connect these electrodes. Basically, you have to create a circuit around your heart to record EKG. This will not be your perfect ECG, but you can easily detect your heartbeats with this. So if the chest is not accessible, this is the way we record ECG, or we record ECG like waveforms. This setup is also used in your Apple smartwatch. You have two electrodes below your like beneath your watch that connects to your wrist. Then you have the crown, which is either your ion negative, ion positive, whatever that they are choosing in their device. Then whenever you want to record the ECG, you start the ECG recording process. You have to place your thumb on that crown, and then only you will be able to record this. This is the way of recording ECG if you are not directly connecting the electrodes to the chest. Then you have the normal chest method. You connect the lead one recording electrodes to your chest and record your ECG. There are other leads also, lead 2, lead 3, and then you have other augmented leads. If you want to go in depth, you can look for ECG leads online, and you will find all the leads. When we call ECG or 12 lead ECG, you don't really mean the leads or the wires coming out of the device or connected to the body. They are basically the signal pathways or polarity of the signal recorded on the heart to create a 3D visualization of the heart in terms of how it is functioning. Then for EEG, we have option of recording EEG easily using gel electrodes on the frontal cortex, frontal part of our head. These are we'll go into the examples, but I'll stop my screen. So I've stopped my screen share. I will go ahead and present you some more information on how to record, how to design your BioAmp, and I will show the GitHub repository also. Okay, let's start with this. This is Texas Instruments Analog Engineer Cookbook, circuit cookbook. It includes a lot of basic operational amplifier designs. That includes your instrumentation amplifier also. On page 27, you will find the instrumentation amplifier, a 2 operational amplifier, instrumentation amplifier design, and they have like explained everything, like RG. This RG sets the gain, then high value resistors can degrade the phase margin, things like that. They have also provided calculation on how to set the gain for your instrumentation amplifier. If you go below this, you will find all the characteristics also. Then you have 3 operational amplifier design, which you can also use for creating your biopotential amplifiers. let's look at, we just look at the output signal from the BioAmp chip pill in terms of how it looks for how it is recording ECG, EOG, EMG, and EEG. If you go into the software section, you would find some filter examples, and if you go in the folder for each filter, you will find at least 2 files that includes your INO file for your Arduino and ECG filter file that includes your band description. For ECG, we are using 0.5 to 0.445 hertz band pass filter, and if you go to the ECG INO file, you will see that we are setting the sampling rate here, and if you go here, you will find 2 references. Go check these out. This includes SciPy signal generate putter filter options to create the coefficients for your band pass filter. Then there is a course from some university. They have created a filtergen.py, basically a Python script that you just have to tell the center frequency, your frequency band. If you are setting the center frequency to 20 and width to be also 20, it will go around from the center. It will take 20 around, or basically you go ahead and check out the filter gen.py for more information. This file will allow you to create these values. You take those values. You also have to mention the sampling rate in filtergen.py, and only for that specific sampling frequency your filter will work. If you want to change the sampling frequency, you have to create another filter. Then we have a normal timer loop, and it works on this sample rate option. So it checks for your microsecond intervals, and based on the value of the timer, it will record a signal at exactly 125 hertz and pass the signal through your filter. It takes the signal every like for each second it will take 125 analog reads. It will send a signal to ECG filter and output the signal. Then this is the very basic example of your ECG filter. Then you can use this ECG filter software to create more sophisticated software that includes your heartbeat detection and heart rate variability calculation, things like that. We have also included heart rate detection. This is a very unique codes, because to detect heartbeats, we usually tend to go with very like sophisticated software that can only be created in Python, or that can only be run on computation intensive hardware like your computer, or a single board computer like your Raspberry Pi. You just go ahead and take a look at this. We have the filter, we have the peak detection algorithm. This is very unique to Upside Labs. You will not find this kind of examples anywhere else. So I highly recommend to check out the software examples for BioAmp GPL. This is the main reason BioAmp GPL is this much successful, because of the software itself. Because the software allows you to do basic human computer interface and brain computer interface designs very easily. You can detect your ECG. Using that ECG, you can detect your heart rate, and using that heart rate, you can detect your heart rate variability. Using that heart rate variability, you can detect heart ailments. So basically, you start with very basic. All the examples are provided. You start with very basic, and you create a very complex project or very complex piece of software that can save a life. 1000 square. It's the same for other filters also. Each filter, it goes from 0.5 hertz to 29.5 hertz. You can create your own filters also, just like I told you. If you go into the software, let's see all the software examples we have available. We have the BLE heart rate detection. This is a ESP32 based code provided by Mateen, our intern. He created this example to send the heart rate detected values to your smartphone, and basically your smartphone has a UUID for Bluetooth, and it can directly show you the heart rate on your mobile phone, even if you don't have any specific application for that. For a glow controller, we created a glow. I will show you the example. Basically, it is a servo controlled glow which you can control using your EMG signals. Then we have drowsiness detection. This is an example created by Padmalya Rawal, our intern, and this uses your eye blink detection algorithm, and it checks for eye blinks. Whenever you are not blinking for a specific period of time, that can be 5 seconds to 10 seconds, depending on your choice. Even if you don't, if you don't blink for 5 to 10 seconds, it will set an alarm, and it will basically detect drowsiness. Then you have basic ECG filter, EEG filter. For EMG envelope, you take the raw EMG signal and create an envelope around that. Envelope can be seen in the I just showed you the video and it shows this envelope. Basically, this is the raw EMG signal, and this is the envelope created around that signal. Then we have basic EMG filter, EOG filter. This is EOG photo capture BLE. This is a very cool set of program. You flash this to your ESP32 and connect it to your smartphone and use the EOG to detect your vertical recording or blinks. And whenever you blink, your mobile phone will click a photo. It's very cool. Then we have EXG visualizer. This is still in progress. Then we have eye blink detection program. We have fixed sampling, basic fixed sampling without any filter. You can use this to design your own biopotential amplifier filters, and you can use it for other applications also. Then we have heartbeat detection, heart rate detection, LED bar graph. Whenever you flex your muscle, you can use this program to use as many LEDs you want, and whenever you flex, the LEDs will show the strength. Then we have servo control, which is also used in a flow controller program. If you don't know KiCad, it is a EDA suite, open source EDA suite, which you can use for hardware design. This is a very great website called learningaboutelectronics.com. On this website, you will find a lot of calculators. One of those calculators is your active inverting operation amplifier bandpass filter. Let's say the cutoff frequency, the low cutoff frequency I want is 0.5 hertz, and high cutoff frequency I want 30 hertz. Then I want the gain to be 1000 for EEG, and I calculate the values for this. You can check. Sorry about that. So when I hit calculate, you will get the result for R1, C1, R2, C2. These are the values you have to use to create a 0.5 hertz to 30 hertz bandpass filter with 1000 gain. These are not the values you will find in normal circumstances. So you have to do some clever mathematics in terms of changing this high pass filter to something else and this low pass filter to something else. Use available resistors, do some practical experiments, and based on that you will find some good match resistors and capacitors that will provide you with the best results for your specific biopotential recording. Then this is the BioAmp EXGPL crowdfunding page or crowd supply page. On this, you will go to these project updates. You will find a lot of information around how to use the biopotential amplifier, the BioAmp EXGPL, how people have used BioAmp EXGPL for their specific applications and things like that. So I highly recommend you to check this out, crowd supply upstream labs BioAmp EXGPL. This will provide you with more information on how to use a device and what are the capabilities of a biopotential amplifier created using basic discrete components can be. Let's go back to the slides now. So let's see the demonstrations or the applications. This is a prosthetic arm created by Mayur Kirish. He is using ulnar nerve signals, and using those signals, he's recording signals, making envelope around the signals, and using the threshold values to control the prosthetic arm. This is an in-move arm. This is an open source prosthetic arm design, a reference design for any prosthetic arm. You can find it on Google. Just search for INMOOV. I think this is the name, in-move. This is me controlling servo claw. This is the files for this servo claw or this type of servo claw can be easily found on internet. You just have to download and print. This is Padmamalya Rawal showing his drowsiness detection algorithm. So when he closes his eye and don't blink for I think 5 seconds, this buzzer and LED will turn. This is a I think 6 degree or 3 degree freedom thread of I think we mistyped here that I think this is 3 degree or 6 degree freedom robot arm controller. You can use any robot arm, but here Chinmay Ronkar used it for his in-house design robotic arm. You have to focus on this one. Whenever you see Aman moves his eyes down, you can see down written here, and whenever he moves his eye up, you will see up written here. So it is a very cool experiment. We have not listed this program yet on the software repository, but we'll do it as soon as possible because this is not well tested in our in-house experiments. This is a very cool example of how you create advanced human-computer interface or brain-computer interface. Here, Ramit Singh Sachar used BioAmp EXGPL for eye blink detection. Then he used Raspberry Pi 0 and Raspberry Pi 0 camera with a battery. And when he detects eye blinks, whenever he detects eye blinks, he sends the signals to the Raspberry Pi 0 to capture an image. And whenever an image is captured, the image will be sent to your laptop. This shows the eye blink detection example. Whenever I'm blinking the eye, you can see the signal and the detected peak. This is the heartbeat detection. Whenever a peak is detected, you can detect it as heartbeat. This is our most recent example using BioAmp. Let's start over and try to look. See John Vivek's eyes. When he closes his eyes, you will see a 10 hertz, clean 10 hertz wave here on the spectrogram. This shows his alpha waves. We are recording from visual cortex, and whenever he opens his eye, the signal goes. So signal is basically disappeared. Now he has closed his eyes. Signal will slowly come up as like either as a streak or a band of streaks. I will replay this for you so you can easily take a look at it again. He closes his eyes and start to see the signal here. He opens his eyes, the signal disappears. So this is a great example of how you can record your brain signals. And if you are able to record brain signals with this much accuracy, you can easily create any brain computer interface. You can use these values as focus values or values for basically controlling a fan, a motor, a LED, things like that. So possibilities are endless, and we highly recommend to check out the Upstream Labs BioAmp project. Everything is open source, everything is open for everyone to use. Just if possible, support us, and if you have any question, you can send us on contact@upstreamlabs.tech. Currently, now I am open for any queries you might have. Please go ahead. Or if you have missed some part of the hands-on biopotential amplifier hardware design and signal processing for your HCI and BCI application pre-workshop, do let me know. I will, whatever time we have, we can visit and discuss some things. Yeah, Dev.
Hi, I have a few questions.
Yeah, please go ahead.
If you have the time. This question is to you, Deepak, and to NeuraAlberta Tech. I'm kind of a little concerned because I've never used this BioAmp pill before. I was wondering, my original thought was to try and use multiple pills because I was trying to get signals out of not only the frontal lobe, but the temporal and occipital lobe also. Now, I noticed that you showed one last example with visual cortex. What would you suggest? I mean, what is the viability, feasibility without any major hardware work going into this during the period of the hackathon? If I wanted to coordinate three pills and probably an EOG as well, do you think that's a feasible thing in this short duration?
Definitely, that is possible. So search for spike recorder. This is a program created by Backyard Brains.
Mhm.
If you go to their store, and search for Pro. So Spiker Box 2. They have a 6-channel of hardware. This is Muscle Spiker Shield Pro.
Okay.
And go to default code for this and go back. I don't want to store this or save this right now, but this is basically a way to convert your Arduino Uno into a 6-channel EXG recording device. The software you are going to download from that place can be used in conjunction with this spike recorder application.
Okay, so
This can be
if
used on
I
Windows. Sorry, this can be used on Windows, your Linux, and on your Mac. But on Linux, you have to compile it from scratch. I'm not sure about the OS X,
okay.
but on Windows it is directly downloadable, and you have a basic Arduino example. So start off with this, save it as a file, Control S, and save it as a file, and start with one channel, record your EEG or record your EOG. When you are ready to go, use the 6-channel option. You can set the channel count there. You don't have to use all 6 channels. If you use single channel, it will provide you with a sampling frequency option for of 10 kilohertz. And if you use 2 channels, it will cut down to half, so 5 kilohertz for both channels. If you use 4,
Mm.
2.5 kilohertz for all 4 channels, you get the point.
Yeah, kind of. So
In addition to that, we are at NeuraAlberta Tech are currently working on some template software or boilerplate software to gang together 5 pills
okay.
and be able to control them through Python. So we're writing the boilerplate code to have that go from the Arduino Uno to Python code, and that should allow you to use up to 5 pills at the same time and coordinate them.
So would that mean that I will not need the spike recorder?
Correct.
Okay. And I think I would need quite a bit of help on this. Any specific mentor I should follow up with in this regard, or should I talk to Upside Down Labs directly?
I am a mentor for NeuraAlberta Tech, natHACKS for
Okay.
session. So I have specific timings, but you can reach out to me or any
Okay.
other mentor available to you. Also, like if NeuraAlberta is creating a 5-channel interface for BioAmp Hardware, do share it as
Mhm.
a pull request on BioAmp Hardware repository. Even they, if you are going to create something new, do
Yeah.
create a pull request on BioAmp Hardware repository. It helps a lot because a lot of people have put it on watch, and if anything special happens, it helps them also and helps us also.
Sure, but I'm not sure I'm fully competent to that extent. So, a question for NeuraAlberta Tech: who should I be contacting regarding this boilerplate, or is it already on the portal?
The boilerplate will be up soon. We are
Okay.
doing some final touches on it. It should be up tomorrow, and
Okay.
the code for the pills and getting the signals into Python is I'm currently working on that right now, so hopefully that'll also be up tomorrow.
Okay.
But it will be, I believe we have a workshop on it at some point, as well as there's a few of us that will be there during the competition and also on Discord to be able to help out with everybody being able to utilize our boilerplate code to help them get started immediately.
Okay. I'm
Eventually.
sorry if anybody else has questions. I don't want to take up all the time. I can wait for any other questions because I have a few more questions to ask. Okay, if nobody else has anything, I'll go on with your permission. The thing is, I'm in Lethbridge right now, and when I go to collect the hardware tomorrow, what should I be asking for? I mean, I'm told I'll be getting 5 of these pills, but will I have to requisition separately for the Uno boards and stuff like that, or how does it work?
I'm not positive, but I believe if you have asked for some pill, and there will be an Uno board supplied with it, if I'm not mistaken.
Okay.
But the people at U of L will definitely be able to help you out there.
Okay.
With that, we definitely did acquire quite a few Arduinos for the express purpose of using them with the upside down lab boards.
So if I'm using 5 pills, what would you, both of you, suggest? I mean, should I go in for multiple boards, or how? I mean, how does it work? Because I've really never tried using multiple A to D converters on Uno before.
You don't, I think, any additional analog to digital converter. Just use the analog pins of a single Arduino Uno and NeuraAlberta.
Right.
If they're creating a software that just takes the signal and sends it over UART, then they have a Python script. You can use that only. Yeah, it will be straightforward.
Okay. So, okay. One final question, though I have a few more. Again, please chip in, NeuraAlberta, because my objective was to try and coordinate this with EOG if possible, and then eventually extract some ERPs. Is that something where I can get some help, some guidance?
I think that, yeah, that would definitely be something where you can get guidance. It's getting ERPs from your EOG is a relatively common task. So I think that there will be a lot of the mentors will definitely be able to help you out with that.
Yeah, the question is, I'd like to synchronize this, like Deepak was pointing out earlier. Well, he did mention the spiker box. You would be reducing the bandwidth if you have multiple channels. I was wondering if I could record these 5 channels, maybe including the EOG, simultaneously. Is that something feasible at all, is what I'm wondering.
Yep. Yeah, that definitely should be feasible. I think the only thing that you might run into is you may need to lower the sampling rate, maybe, but I don't think that you would. But that would be the only issue that I can think of off the top of my head.
Actually, you are right.
Okay.
You will have anybody using 6 or 5, even 5 BioAmp pills with Arduino Uno, with basic Arduino code. You are not fiddling with the bits. What Backyard Brains has done, they are setting everything using registers, and you're able to get very fine-tuned timer controlled output to your spike recorder software. If NeuraAlberta is creating a basic Arduino code that just is taking analog inputs and sending it over UART, they are not. I'm not sure if they are using registers to control. Please correct me if I'm wrong. They might not be using register controlled timer functions to precisely time the sampling frequency for the input signal. So if you don't precisely control when your signal is being recorded, your filters will not work, and that is something you have to keep in mind when you use more than one biopotential amplifier. Keep the sampling rate to be around 250 for your EEG and EOG application. You will be good to go with 250. If you go something like 1 kilohertz with basic Arduino code, you will find a lot of noise in the output after filtration. It will be clean before filtration, but after filtering, it might be noisy because your timing is not correct. So timing is very crucial if you are applying your software controlled band pass filters. Also, NeuraAlberta, if you really need any help from Upside Labs, we'll be glad to do that, and we can set up a guide or something like that on the repository, and we can provide the information to other students who might be dealing with the same problem.
Definitely, yeah. I believe we currently are not working with the registers, and so I believe the timing will be a bit of an issue. I'm not positive on how much of an issue. It'll be for which tasks, because we haven't had enough time to test it out, but we currently won't be doing that.
Agree. So what I really recommend you to do is use to use this fixed sampling example. In this,
Okay.
you just change the sampling rate to 250, and
Okay.
you will record input signal from all the 6 in input pins, and you just send the signal on the UART. Then you can use any Python program to get the signals as either comma separated values CSV, and you then split the values and do your filtering there. Other option I was thinking, you use what Backyard Brains has provided for multiple channel recording, and if you see, they have used registers for everything. So this is very optimized even to the ADC bits and everything. So both options are good. If you are just recording at 250 hertz, this will be a good option because it saves a lot of time. And we are currently trying to debug this to be used with other boards like ESP32. ESP32 is much more powerful, as in it has a very high operational frequency. So whatever we are going to do with the timing functions will be obsolete, because the CPU frequency is so high, it doesn't matter if you are going to use registers.
Okay.
Yep. And if you have a Raspberry Pi Pico, use that with some resistors. Or for EOG and EEG, we tried without resistors, as in your voltage divider resistors to convert the 5 volt signal to 3.3 volt. Without those resistors, it also works great, and you get a 12-bit like resolution. Although the ADC of Raspberry Pi Pico by default is bit noisy, you have to check the data sheet to connect one pin, the analog reference pin, to I think BCC to make it better.
Okay, thanks a lot. Just if I can just ask 2 more questions quickly. One
But
is if I need to capture on an Android for some outdoor activities, let's say, you mentioned there was a device where the mobile would take snapshot or pictures of whatever this person was looking at. What's the interface between the pill and the Android?
so if you want to record from a single BioAmp chipel, there is an option to use the microphone input of your uh, mobile phone, and
Okay.
the spike recorder software is also available on your sorry, on your iOS devices and iOS, basically Apple Store and on Play Store. You can download that. Then go to Upside Labs. Go to this sheet, hardware. There should be a PDF in here. I will have to, I think, look for it and include it in the repository.
Okay.
So basically, you have the option to create microphone to BioAmp chipel interface, and you can record from any like you can record from plants. Your human signals can also be recorded using that.
Okay, thanks. And I'll end it off with just one final question, and I'd like you to comment on this. What about using open source EEG lab software?
That
Any
is
thought on that?
possible. Yeah. So basically, one scientist from Russia is using EEG related open source. It is an open source software, I think, and he provided me with the Arduino code. You contact me if you want to use any open source software for specifically for EEG. I will also provide the software to NeuraAlberta if somebody else wants it. Keep in touch.
And the software that we've been using at NeuraAlberta is called BrainFlow. It's a library. We also have one of the mentors is the maintainer of the BrainFlow library. So that's also a good resource.
Can we use the BrainFlow with Arduino?
I am not positive. I think it takes a little bit of interface code to do it with Arduino. So partially, once it's translated, I think you can do a good bit of work with BrainFlow after converting over to an appropriate type.
Okay. Let me check what that scientist is using. I think it is BrainFlow. It is BrainBay. And I have a basic Arduino example code for that. So if you want to use BrainBay, you can use that with BioAmp.
Yes, Deepak. So your boards are quite small, and so I was wondering if, so it appears that making sure that they're small is quite important to you and your company. So I was wondering if, when you were designing the boards, did you end up having to cut off certain functionality that you wanted to add in, but it would have made the board larger than you want it to be or more complex than you wanted it to be?
Yeah, one functionality which we removed is kind of debatable. We removed the input protection diodes. Those are not necessarily needed for our specific application for basically how we are using the device, how we are treating the device. Other than that, not much is removed. If you are going to use a specific biopotential related scenario, like for ECG, we usually tend to go with active DRL, driven right, like that takes the midpoint from a 3 operation amplifier gain resistor and then supplies to a buffer with a reference input. So it is tend to provide you with better results, but what we are getting with BioAmp is far more better than what we can achieve with the DRL. So we are not compromising with the signals at all. And you are saying that BioAmp is quite small. Actually, we made it bit bigger so that it can be handled easily. We were thinking of shrinking it more, but we stopped at a point. Yeah.
That's interesting. Thank you.
Yeah, we are going to release a new hardware which is based on BioAmp. It is a proprietary hardware for our different company. It is going to be very minute. We are going to use a 0402 resistors and basically take half of the BioAmp or even smaller than that. It will be a module for EMG signals that can be included in prosthetic arm controllers. You just put it as a chip and it will have only 6 pins. It will simplify the design of EMG controlled augmentation devices, prosthetic hands, game controllers, and things like that.
Cool. Well, I'll have to definitely keep my eye out for that. It sounds like it would be fun to play around with.
Definitely, we'll send some samples to NeuraAlberta as well.
Awesome. Well, I think we should wrap it up there. Thank you so much for your presentation.
It was a pleasure.
It was fantastic having you on, and I think you did a great job at presenting your product, and it's a really cool board.
Thank you so much. Okay. Thank you so much, everyone. Have a good one. Stay safe.
Thank you. You too. Thank you so much.